Hello everyone, my name is Meining Du. I'm from the University of Hong Kong in China. The title of the paper I will be presenting is Approaches to NMR Sensitivity Enhancement based on Theoretical Analysis. The presentation today could mainly be divided into 6 sections: Introduction, Theoretical Principle, Traditional Approaches, NMR Hyperpolarization, Limitations and Prospects, and finally the conclusion. For introduction part, the main object of my research is the nuclear magnetic resonance, also called NMR. It is a powerful tool to explore the internal structure and composition of substance, and has been broadly investigated and applied in many industries, such as medical treatment, food safety, and materials. However, the relatively low sensitivity is a severe problem prevent the further application of NMR, because it will make the concentration of samples required high and the collection time long. That's why my research aim is to suggest various approaches to deal with this defect. I will cover traditional approaches which adjust factors based on the theoretical principle, and then the progressive hyperpolarization method will also be mentioned as well. For each method, the explanation of theoretical principles, research status, and its future development trend will all be discussed and analyzed. For theoretical principles, NMR is a physical phenomenon based on the charge and spin properties of nuclei. The magnetic spin is always distributed randomly of the same energy without an external magnetic field. As the field applied, the spin of nuclei will align with the field and will be either parallel or antiparallel to each other. Hence, the energy levels has consequently been split. At the same time, the axis of rotation of magnetic spin also precesses around the direction of the magnetic field with Larmor frequency. After separating the energy level, radio frequency pulses are introduced, which match the value of the Larmor frequency. The nucleus at a lower energy level will absorb this radiation and go to a higher energy level with resonance occurring. That's the working principle of NMR. The low sensitivity of NMR is actually an inherent problem due to the small number of population differences, also known as the polarization of nuclei spins at thermal equilibrium. To improve this inherent problem, there are 2 common strategies. One is to increase the magnetic flux density of the external magnetic field, and the other is to decrease the sample temperature. However, the increment of magnetic flux density is restricted owing to imperfect superconducting technology, which leads to high cost and a complicated manner. The decrement in T to a significant amount is only possible for particular sample types. All these limitations of these 2 traditional approaches encourage the discovery of further method, namely hyperpolarization. The working principle of hyperpolarization method is to increase the population difference between higher and lower energy levels from thermal equilibrium by transferring the hyperpolarized state of exogenous particles to the atomic nucleus of the target molecule. It could mainly be divided into 2 general cases according to the polarization sources, and could also be classified into more branched fields as shown in figure below. For my research, I chose and analyzed 3 representative and frequently used methods, which are DNP, OP, and PHIP. The first one is dynamic nuclear polarization, DNP. The principle is mainly the polarization transfer from electron to nucleus. Actually, the electron and the surrounding nucleus have dipole-dipole interaction. When the microwave irradiation near Larmor frequency applies, the spin direction of both nuclei and electrons will undergo reverse. For this case, the difference between the number of particles between the energy levels increases, and the polarization hence to be increased. In fact, the polarization of electrons is about 660 times that of protons, so the spin polarization of nuclei is greatly strengthened by the higher polarization of corresponding electrons. Thus, this kind of change in the distribution of nuclear spin energy level has led to greater polarization and better sensitivity of NMR. For application, due to the high sensitivity provided by the NP, MRI could obtain high-resolution carbon-13 images in a small time interval. It could also be well applied in analyzing material structure with active surface size of low area and concentration, which are usually trapped in the spectral resolution. The next one is optical pumping, OP. It changes the nuclear spin distribution in thermal equilibrium and uses circularly polarized light to realize nuclear spin hyperpolarization. In my research, I chose a widely applied subfield called spin exchange optical pumping, SEOP, as an example to illustrate OP. SEOP is an indirect method that uses alkaline metal gas as a medium to realize the hyperpolarization of the noble gas. With the existence of magnetic field and laser, the electronic energy level of the rubidium atom is split with electron transitions. This results in the imbalance of number of electrons at the ground state. Moreover, the electronic spin of rubidium atoms and the nuclear spin of noble gas atoms would form van der Waals molecules in the process of spin exchange. Thus, the detection sensitivity of noble gas would consequently be increased. Due to its high natural abundance and fast spin exchange rate of xenon, it is usually used as aforementioned noble gas in SEOP. Because of its strong sensitivity, this method is often used to detect in situ catalytic process and the structure and connectivity of porous material in the chemistry industry. Moreover, it is also a potential technique for medical use and research in biological protein. The final one is PHIP. The operating principle of PHIP is to increase the sensitivity of NMR by adding enriched pyrohydrogen to the unsaturated group of the substrate molecules through catalytic hydrogenation. This will increase the spin population differences and hence achieve the effect of hyperpolarization. Taking advantage of low equipment costs, simple operation, and high polarization efficiency, it could be utilized to study hydrogenation reactions, catalytic mechanisms, biological metallic reactions, and enhance contrast medium in MRI. The next section, limitations and prospects. For limitations, the researches could also be extended to other hyperpolarization aspects, like chemically induced dynamic nuclear polarization, which occur in optical excited or thermal excited chemical reactions, and photo-CIDMP, will occur non-Boltzmann nuclear spin polarization under illumination. Although hyperpolarization plays a vital role in improving sensitivity, it could also have some drawbacks that restrict its further development and could be considered feasible in future investigations. Firstly, the lifetime of hyperpolarization should be extended and prevent premature relaxation. Another limitation of hyperpolarization is that it cannot provide the relative concentration of a particular substance by simply integrating peaks, because it involves polarization transfer and relaxation. Therefore, it should be reformed to retain this valuable property. Moreover, expensive and bulky NMR equipment for hyperpolarization occurs, and the store could be another severe problem. Hence, finding ways to increase the sensitivity of NMR and simultaneously have a low-cost and portable form could be worthy of consideration to promote more comprehensive application. In summary, this paper begins with an explanation of the concept of NMR and describes the basic method and powerful approach, hyperpolarization, to improve the sensitivity of NMR. For each section, its theoretical principles, application branches, and prospects are analyzed successively. From the discussion in this paper, the high cost and small increase brought by the uplift of the magnetic field strength and reduction of the temperature can be well solved by the hyperpolarization method, and further innovations could solve specific deficiencies which enhance the detected sensitivity. As more precise instruments and more advanced methods have been used, the problems that restrict the further improvement of sensitivity will be solved more effectively. This progressive method will be more extensive, and more practical in distinct fields. That's the end of my presentation. Thank you for listening.